Model railway automatic block signaling using Arduinos. Are you contemplating adding signaling to your layout? We're going to take a journey from wondering how is signaling done on the railways to how can I apply this on a model railroad layout. There's several approaches on a model railroad. Turnout signaling is probably the easiest, where you're using the single pole double throw switch on a switch machine to control turnout signaling. Then there's manual block signaling and automatic block signaling, which is the focus of this presentation. Well, what are my options for implementing on a layout? They're commercial systems, and we're going to focus on do-it-yourself signaling systems using Arduinos. At the end of this presentation, we're going down the rabbit hole. I developed an ABS diorama for Modeler's Corner at train shows. And then further down the rabbit hole, I developed a proof of concept passing siding simulator. And then on to expand into other layout design elements. Well, how is signaling done on the railroad? Ian Juby, who's a conductor, has a 4-part YouTube video, Farmer's Guide to Reading Canadian Railroad Signals. A diagram of Canadian signals with 3 heads is on the right. You can see some are aligned and others are staggered. Signals directly above one another equals controlled by a human. Red over red over red is an absolute stop. You must check with the dispatcher to proceed. Staggered signals are controlled by an automated system. Red is permissive stop. Stop, look, listen, proceed if reduce speed if all is okay. So the 3 signal heads, top is meant for high speed as defined in the rule book. The middle is medium speed, 30 miles per hour, generally used with going through widening, diverging curved turnout routes. And then the bottom is slow speed, going through a sharper diverging curved turnout route. Green over red, clear to proceed at high speed. Flashing yellow over red. Well, an advanced clear with expected stop in 2 blocks. Solid yellow over red. You're clear to stop at 1 block. Red over red, clear to proceed at medium speed. Red over red, clear at medium speed to stop in 1 block. Ian tells us that RTC is rail traffic control, and in this system, a dispatcher communicates with the engineer by radio and through manual block signaling. CTC is centralized traffic control. The dispatcher communicates through routing signaling and automatic permissive block signaling in stretches in between turnouts. Usually this is sort of long stretches. The train's location is monitored using current detection track relay circuits. The wheels entering the block shorts out the relay. Green signal drops to red. Fail-safe mechanism in this system, a broken rail or if power is lost, the green signal drops to red. Signals are generally located at 2-mile intervals to give a long train enough time to come to a stop. 2015, each signal head cost $20,000 Canadian. So how does the railway save money? Well, you drop to 1 signal head when you have long stretches at high speed with no turnouts. When you do come to an area of turnouts, you then have 2 signal heads. The upper is the high speed through route and the lower is the medium speed diverging route. A single head with an A sign below equals RTC controlled. Red is an absolute stop. The engineer must radio the dispatcher to get permission to proceed. Without the A sign, it's CTC controlled. Red is a permissive stop. Stop, look, listen, proceed with caution. Well, moving all of this into model railroading. The NMRA Operations Special Interest Group has developed a compendium of model railroad operations. They note that turnouts at CTC are called control points. Control points are controlled by the dispatcher. And then in between these control points, we have intermediate signals that are controlled automatically. Eastbound signals are assigned even numbers, westbound odd numbers. Turnout signals have two heads. Upper has 3 colors, the lower has 2 colors. Again, yellow through the diverging route. Dave Abels has a nice guide to signals and interlockings. You can get it on Amazon in Canada at Indigo Chapters. Interlocking routes started with hand levers replaced with electrical mechanical systems. Absolute permissive block signaling for single track main lines, absolute stop and stay for opposing trains, and permissive for following trains. Dave describes how to use commercial systems for train detection and signaling, and goes on to describe how to use computers to control road traffic on a layout. Scott Goth has a nice series of railroad signaling primers for model railroads that he's done for the northeastern region of the NMRA. Let's see, Part 3, route-based signaling and interlocking. Part 4 was done this year, taking a modular approach. So he talks about putting signaling on modules that one takes to train shows. Well, how can I apply this on my layout? For train location, current detection, like the railway. Caboose era, you have a lighted caboose at the end of the train, so the locomotive moves into the next block. Our caboose is still in the current block here, so our block remains occupied. A bit of a problem though in the era after they dropped cabooses. We need to install resistance wheels. It's on rolling stock. Passenger trains get lighted passenger cars. Signals. 3 head signals need to be custom made. 1 and 2 head signals are commercially available. Double head signals, well, the lower head generally has 3 colors. I tend to ignore the green. Upper head is used for the main line through route, high speed. Lower head for diverging route, medium speed. And by the way here, if something goes wrong with the signal and it's dark, then that's an absolute stop. Call the dispatcher. Well, layout signaling approaches. The simplest one here would be maybe a layout-based one, starting with turnout signaling. And this can be controlled through the single pole double throw switches, usually part of switch machines. And there's block signaling and a combination turnout and block signaling. An RTC approach, you have a dispatcher in another room, controls switches, and sets intermediate signals based on communication with engineers. So that's a manual block signaling system. Often single head signals. Red is an absolute stop. The engineer must radio the dispatcher to get permission to proceed. And then there's a CTC approach. The operator controls the switches, and the layout uses, or the system uses, current detection to adjust the interlocking signals and control the block signal systems. Well, a Google search for commercial systems. Here's a list that I came up with. Commercial signals, 1 and 2 head, and where one can get them. Custom signal systems is exactly what it is. It customize your signal order. Well, is there a do-it-yourself option? We're going to go down the rabbit hole. Yes, signaling using Arduino microprocessors. I built an ABS diorama to just demonstrate automatic block signaling at Modeler's Corner train shows. And then this led me down the rabbit hole, triggering the ABS simulator as proof of concept for passing siding layout design element. And that then further down the rabbit hole into developing the ABS installation guide for other layout design elements. In September 2024, I finished building a demonstration automatic block signaling diorama for Modeler's Corner at train shows. The length of the diorama was limited to 38 inches for the space available on the table. There is an unmonitored block at each end for the switches to sit and 4 monitored blocks in between. Monitoring is done with a current sensor. Each block has an Arduino Nano and an NCE BD20 current sensor. The 4 nanos are linked by wires to communicate their occupancy state to the other nanos. Note that block 1 has no previous nano and block 4 has no next nano. These 2 blocks required a modification to their programs, called sketches in Arduino language, to pretend that the unmonitored blocks at each end are clear. How might we apply this ABS demonstration to a layout? Adding a passing siding between blocks 2 and 3 produces a basic layout design element with turnout blocks on each end of the passing siding. Blocks on a layout will likely vary in length and be much longer than those on my diorama. A point-to-point layout will be similar to the diorama in that one end will have no previous nano and the other end no next nano. In a loop layout, all nanos will have a previous and a next nano. How might I build a proof of concept ABS with passing siding? An actual diorama would be too long for Modeler's Corner, so I decided to build a simulator where the nanos, relays, and signals would be positioned on a legal-sized diagram. In the diagram, block 1 has no previous nano sketch, and block 4 has a no next nano sketch. Blocks 2 and 3 are the new turnout blocks with wire connections from a simulated switch machine's single-pole double-throw switch. Each turnout nano controls a 4-channel relay, in which channel 1 controls frog polarity, channel 3 switches previous block communications between the mainline and siding nanos, channel 4 does the same for the next block communications. Each turnout nano also has direct links to the mainline and siding nanos to communicate switch orientations to assist in determining if the nano has a previous and a next nano. A wire from pin 10 on the nano is connected to the nano's ground to simulate that a block is occupied. 3-aspect single-head signals guard the entry to blocks. Standing at the east end on the left side of the diagram facing towards the west end, signals with a numeral 1 suffix in sketches are on the westward signals on the right or lower side of the diagram. They have a WS prefix in the diagram. Those with a numeral 2 suffix in sketches are eastward signals on the left or upper side of the diagram. They have an ES prefix. The entrances to the main line and siding blocks are different. Their 3 aspects, double head signals, add turnout signalings to block occupancy signaling. The upper head is for mainline status and the lower head for the siding status. Next up is an animation of how the simulator works, showing only the eastbound signals to simplify the animation. Before showing the simulator in action, let's review the electrical components. The image being displayed now is the nano pinout diagram. If you aren't familiar with Arduinos, I recommend that you watch Greg Williams' YouTube Introductory Clinic. In YouTube, search for nmra.org. Then look for live, and then search for February the 25th, 2005. Slide the slider along to 1 hour, 19 minutes, 19 seconds. The next major component in the project is a current detector. The image you are viewing is the NCE BD20 for DCC layouts only. Circuits for Tracks makes an occupancy detector for DC as well as DCC. Turnouts require 2 additional components. The first is a 4-channel optocoupler relay. The optocoupler separates the 5-volt section at the bottom of the image that is driven by the nano from the potentially high voltage going through the screw terminals at the top. Channel 1 controls frog polarity. Channel 3 controls communications to the previous nano, and channel 4 communications to the next nano. Turnout block sketches require more pins than are available on the nano. This input-output pin expander provides the 6 additional pins that we need for signaling. Time to run the simulator. This jumble of wires is an automatic block signaling simulator that I built to work through how one might install a do-it-yourself automatic block signaling system on a layout. Things are a bit crowded on this simulator because I'm having to position it on a legal size paper. On a layout here, the blocks are going to be at least a couple of feet in length. So let's walk through the simulator. There's an east side. We have an entrance block here, turnout block. We have a main line and siding blocks, a second turnout block, and then a west end ending block. There's not enough space for signals in both directions, so the signals that you see here are all for eastbound traffic. Over here we have the power input, voltage converter, 5.2 volts, power going to nano microprocessors. You can see the lights flashing on them here. With the turnouts here, we have relays that are going to control frog polarity and communications between the nanos. When we activate a a switch here, you're going to see that the LEDs come on when it moves to the siding. Now on a layout here, you wind up that we would be using something like current detection. We could use point detectors, but very often it's current sensing. We're going to simulate that then by connecting a pin on the nano to ground. For the switches here, we're also going to simulate that here with connecting a pin on a nano to ground. On a layout here, you would have a single pole double throw. Switch would then sort of current if it's in, let's say, diverging route, no current if it's in the mainline route. Well, let's begin to sort of work through. Oh, I should sort of mention here, these two signals are supposed to be one. The green is the upper head and the red one is the lower head here. And this is for the turnout block 2. In this case here, these are the signals for leaving the siding and the main line. So this one is the main line and that one is the siding here. At the moment here at startup, the turnouts are switched on both sides, are set to main line. Okay, let's walk through things here. We're going to simulate a train coming in from the west. Here it's going to go into the siding, and then a train's going to come from the east, go into the main line, and then we're going to switch the turnout 1, and this train in the siding will leave and exit on the east, and then we'll switch the turnout on turnout block 2, and the train will move from the main line and exit on the west here. So here we are, train is coming in from the west here, so it's now on block 4, and the entrance signal to block 4 is now gone red. Here, before we move from block 4 to block 3, here we're going to set the turnout. Okay, so the turnout's been set. You can see the LEDs have come on here on the relay here, and so the signal for the upper head signal is now gone red because you can't go through in the main line, and the lower head signal has gone to yellow. Here we want the engineer to go into the siding at a slower speed here. So now we'll sort of move into that turnout block here, and we'll move out of that there. So we're into block 3, and the entrance signal to that's gone red, and the preceding signal now is yellow. Moving on in here into the siding. Here, so we've now got a train in the siding, so upper head and lower head are red. The preceding block, the turnout block, is now yellow, and block 4 is now green. So we're in the siding. We're now going to have our train from the east arrive. Okay, well, we're in block 1, and so if you were, remember this is eastbound, so if you were in block 2, you can't come into block 1. There's a train there. We're now going to go into the main line. Here we're in the turnout block here. So if we're in the turnout block, here the main line is set to it, so it's now red because you can't go into the turnout block. But if you're in the turnout block, you could go into block 1, so that's green. Okay, now we're going to go into the main line. Okay, so we've left that. We're on the main line here. You wind up that a train on the main line could go into turnout block. That's why that's green. Okay, we're now going to flip the turnout. Okay, so the LEDs have gone there. We're in the siding here, and we've flipped that so the main line exit going east is now red, and the siding is now green. We can go into block 2. So let's do that. We'll go into block 2. Okay, so that's now red. Here we're in block 2. So the entrance to block 2 is now red here. I'm going to switch turnout 2. There we go. Okay, so we've switched turnout 2. It's now, the LEDs are out here. So let's see. If you're going here into the main line, there's a train there, so you can't go there. And we're against the siding, so it's red. We're just going to take the train out of the oh, maybe we'll move the train from the, okay, we'll take the train out of the siding and into the turnout block 1. So we'll take it out of there. Into block 1. So that's red here now because we're in the turnout block, so you can't come into that. I'm going to move into the other block 1. We'll come out of the turnout block here. So turnout block 1 heading east is occupied, so we can't go from block 2 to block 1. We siding here, we could go from siding, slow approach into block 2. Where here, we're going to get out of get the train out here. Okay, so the train has left here, so you can go into block 1, you can go into block 2. Now we're going to get back to our westbound train here. And it's going to head into turnout 2. So we'll go into turnout 2, leave the main line. There we go. Okay. Okay, so here we are, we're in turnout 2. So the entrance to turnout 2 is red. This is the double head one, so we're set up for main line, so that should be here, and we are currently in yellow, so we can come in there. And we've got a yellow saying here that the next signal is going to be red. That's because the turnout is set against it. Here, the LEDs are on. So if we wind up switching back to that, here, we wind up here, it's now set to main line. So the main line signal is green. So if you were going in this direction here, green, green, green. Okay, let's continue our travel westbound on. There we go. So entrance to block 4 is now red because we've got a train in it, and now we leave. Here, so we're back to green, green. We're set to main line. Upper head is green, lower is red, and we can leave. Our turnout is set for the main line, so that's green and that's green. The Arduino provides a do-it-yourself option to commercial systems for automatic block signaling. Other layout design elements include a spur, branch line, yard entrance with a runaround track, yard ladder, off a siding, reversing loop, Y, single crossover. Now some special layout design elements include diamond crossing and a double crossover. Well, for the spur here, you've got one turnout block, in this case turnout 2 block, and it's on the through side here you've got a main line. On the diverging route side here you really just have an extension of the turnout. For the branch line or industrial siding, you're going to have much longer track here, so you've got one or more blocks here. The end of that line is going to be a nano 4 or a nano 1, depending upon the orientation of this turnout block. Yard with a runaround. So here's our runaround here, main line, passing siding. You got a turnout, and then here's the yard ladder. In between the turnout and the yard ladder, you're likely going to have a nano 1 or a nano 4 so that the yard itself is unmonitored. This is a different variation where the yard ladder is directly off the siding here. It really shouldn't be part of the automatic block signaling here. For automatic block signaling, your control points are at the start and at the end here. Signaling here is essentially a separate turnout signaling system. Okay, reversing loop. Here the sketches connect these two blocks to behave as one. In this case here, you wind up that everything here is the next nano for turnout 1. A Y. So it's essentially a modified siding. So we've got a turnout 1, mainline turnout 2. And the diverging routes here, you wind up the tail becomes the siding. In this case here, you want the entrance signals to the siding are essentially the lower head here of your double head signals. Single crossover. In this situation here, turnout 1 block's next nano is turnout 2. So the lower head here is actually controlled by turnout 2. Turnout 2's previous nano is turnout 1, and the lower head of its double head signal is controlled by turnout 1. So the opposing turnout is the siding and controls the double head. The diamond crossing. We essentially have two routes, CR1, CR2. CR1A and 1B are joined in a sketch as if they were one. Similarly, another sketch joins CR2A and CR2B. Now a train coming in this direction here, triggering CR1B, here will set all of the entrance signals to red. Double crossover. It's somewhat similar to our single crossover, in which here the entrance signal on the lower head here is controlled by turnout 2, behaving as a siding. Well, the weakness of the current detection block occupancy is that as the locomotive enters block 2, the rest of the train is still going to be in block 1. It'd be nice to have cars with low current flow between the rails in block 1, such as a lighted passenger car or a lighted caboose. Little complication if we're modeling the post-caboose era, so we need to put resistance wheel sets in all the rolling stock. That's the preferred solution. Here, you never really know which car is going to be at the very end, so you have to do every single one. Poor man's approach to that would be the train delay variable within an Arduino sketch. So you figure out the average time to clear a block, and you put that, you adjust the beginning of the sketch in the declaration section. A little bit of a problem with that is that if you've got, let's say, a long block, you've got a long train that's going to take longer than the average time, then the block is still occupied when the signals go green. So a combined current detection and point detection using maybe laser sensors is the best solution, but high cost and very complex sketch coding. Talking about sketches here, this is the basic framework. We have a declaration section. This is where you assign the pins, identify variables. We move into the setup section. Okay, we've got a pin. Is it an output pin or an input pin? And then we assign values to variables, such as, we start off with val A1, so that's what's the occupancy in our current block, set to 1 equals clear at the start when everything's just turned on. And then we set up 5 signal states. Here we've got green, 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 yellow, yellow, green, yellow, yellow, and red, red. The first letter in GY is green is for the east or left side entrance signal. Y is for the west or right side signal, entrance signal. And then we move into the void loop, which is essentially a program racetrack. Here we get our block's occupancy status. What's the previous block's status? What's the next block's occupancy status? We send all of that information to the signals, one of the signal state functions, and we return from that, pause for the train delay, and then loop back to the beginning. And that signal state function here, we first set the signals, and then we take the value for A1, A2, A3, combine them, and find out what's the next signal state, and head back into our program track. Entering the void loop for the first time, our signal state is going to be green, green. We get our block's occupancy state. We've got a high voltage on pin 10, so our block is clear. We set val A1 therefore to 1. We're going to talk to the previous nano and the next nano. We notify the previous nano that our block is clear. We then read the previous nano's block state. It had a low voltage on pin 10, so it's occupied. We set val A2 to 0. We notify the next nano that our occupancy state is clear. We check and read what the next nano's occupancy state is. And it's got a high voltage on pin 10, so we set that, so it's clear. And we set val A3 to 1. Well, now we're going to call the green, green signal state function. And it sets the signals and then takes the val A1, val A2, val A3, and finds the signal state for that combination. In this case here, 101, signal state is green, yellow. We're going to loop back to the start. But before getting there, we need to wait for the train delay timeout. Okay, so now we've returned to the start of the void loop. At this time here, our signal state is green, yellow. We check the block occupancy state on the current detector. We've got a low voltage on pin 10, so our block is now occupied, and we set val A1 to 0. We notify the previous nano that we're occupied. We check the previous nano. It's got a high voltage now on pin 10, so it's clear. And we set val A2 to 1. We communicate with the next nano. We tell it that we're occupied. We're then going to read the status of the next nano, and it's got a high voltage on pin 10, so it's clear. We set val A3 to 1. We're then going to call the green-yellow signal state function. And we've got combination val A1 plus val A2 plus val A3 of 0, 1, 1. Our next signal state is red, red. We're going to loop back to the start here, but again, we'll wait for the train delay timeout before returning to the start of the void loop. Well, if you want to learn more about Arduinos, I suggest you go to nmra.org, type in live, go to the live section, search for February the 25th, and then you slide along to 1 hour, 19 minutes, 11 seconds for Greg Williams' Introduction to Arduinos. The end here, Greg observes that Arduinos is something we can all learn to use. If you want hands-on experience so that you can maybe modify sketches or develop your own, I suggest you take McWhorter's courses here. So you can search for McWhorter in YouTube or go to his website here, www.techboy.com, where you'll find links to his YouTube courses. You purchase the SunFounder Elite Kit from Amazon to work through the courses with him. And then you can enhance your learning through other people, such as the DroneBot workshop. You go to the Eastern Canada Division website. There's some articles on signaling and train detection. It's located in the Welcome to the Hobby section. And that's the end.